Folks, welcome back. Hopefully that short break gave you enough time to get yourself a cuppa, whether it's tea or coffee. Either way, I want you caffeinated and fully at attention to listen to Giles, because he's here to introduce us to something called media streaming mesh. Giles, I'll waste no more of your time. Take it away.
Thank you so much. Hopefully we can bring slides up. Great. So yes, hi, my name's Giles. I work for Cisco, but in fact, this talk is about an open source project that I've been working on for a while, called Media Streaming Mesh. And I guess the sort of 50,000 foot view of it is the goal is to enable Kubernetes to support real time media apps to the same quality that it does web apps today. So without further ado, this is interesting. The slide doesn't quite fit on the left. It should say, "Don't text me before I've seen the goal." And really, this is where a lot of this came from. I don't know if anyone watching this has had this same experience, but I've certainly had it on many occasions where I'll be watching a match and perhaps I'm watching over the top and my friend is watching on satellite or cable. And the problem is, of course, my friend texts me to say, "Wasn't that a great goal? Harry Kane scores again." And I'm like, well, actually, I haven't seen it yet. So thanks for that. And so I guess the thing is, we know that we can do real time over the internet. I mean, I'm presenting this real time to you now, but for some reason, when I watch the football, it seems to lag by 30 or 40 seconds. So I suppose the question is, well, why is that? Well, it turns out this is really hard. The challenge, of course, is that you want to scale this out to millions of viewers at a time. And you can't really do that using one centralized media bridge. You're going to have to distribute stuff using a content distribution network. And that way you're positioning content closer to the users before you then send it to each user. And I think that the challenge there, of course, is that content distribution networks today are very much based on web proxies. And so what we think is real-time streaming over the internet is actually going through a series of web caches where my browser pulls something or my TV pulls something, the proxy pulls something from the next layer, and so on and so on, and hence the delay. So I suppose my contention is that we really need to find a more cloud-native way of distributing content in real time using more of a push-based mechanism. And certainly there's a lot of buzz in the industry these days about edge compute. And so it feels to me like this could be an edge compute use case where rather than distributing the content through a CDN cache, those same hardware platforms, as well as running CDNs, could run apps that would distribute the video in real time. And of course, that's not the only use case for this technology. As I said at the very beginning, the goal is really to support any real-time media app in Kubernetes. And so I'll come on to some of these other use cases too. This is interesting. The platform doesn't do the build, so that's going to be interesting. So these slightly misaligned circles from my PowerPoint deck. I guess what I would say is that Kubernetes is very much based around web applications. Now, if you divide the world of applications using a taxonomy, and here I've used a 2x2 taxonomy since that's what people who do MBAs and workers management consultants seem to love to do, then web applications are firmly in this non-real-time interactive quadrant. And so this division into non-real-time, so that is clearly apps that aren't isochronous, so there isn't a fixed timing. Real-time, so things that have those real-time characteristics, but equally importantly, dividing things into interactive, so things that have request-response semantics versus streaming, that is having pub-sub semantics. And so web apps are very firmly in that top left corner, but in fact, what we want to address here with media streaming mesh is very much the bottom right corner, so live media. And for live media, that could be anything, as I say, could be distributing football, could be IoT cameras, could be audio, could be anything really. But what we focused on initially is anything using the real-time protocol or RTP, just to give us the right kind of scope of focus for this project. But really the same mechanisms could be used for anything that's streaming over UDP. And it's also worth saying quickly that I've called this fuzzy because to some extent, the division between, for example, interactive and streaming, in this case, if I'm in a WebEx or a Zoom, I might feel that I'm interacting with people, but actually the application underneath is very much streaming. So I'm streaming my content to the other viewers. Equally on non-real time and real time, the distinction there can be quite fuzzy, because taking the football as an example, the lag of 30 seconds, is that real time versus watching on cable or satellite, where in fact you still have a couple of seconds of delay typically. And really that's a modern thing. So I'm one of those people who's old enough to remember the old days when, oh, it is this way around, good. When you'd be watching the news or watching TV, the news was about to come up, it would count up towards the hour. That was the days of analog TV, and of course we don't have that anymore, simply because there is a delay in compressing and decompressing the content. So looking at how we distribute live video, and again, apologies for how this platform seems to have shown the PowerPoint. I guess there are stages from the camera to the client. So the camera feeds get sent to the studio, and that could be, again, the football example, you might have a bunch of cameras at the stadium. Maybe you've got an outside broadcast facility, so you're only sending one feed back to the studio, or maybe you're sending them all and then picking one at the studio. Either way, you're picking one camera view to show. You're probably sticking something on the top that says, here's the score. Maybe there's some news at the bottom. Maybe even you have things like subtitles, perhaps less so for football. And once you've got that kind of canonical format that you're going to distribute to your clients, what you need to do is to effectively reformat that, because that typically today is 4K HDR, uncompressed. Now that's something like 12 gigabits per second, and clearly I'm not going to stream 12 gigabits per second to my television. So what you're going to do is encode into multiple formats in terms of the resolution, in terms of the bit rate. You're going to add on content protection. And finally, then you'll distribute out to CDN caches in the over-the-top case. But equally, it could be, cable head ends, IPTV head ends, broadcast towers, satellite networks, etc. And then finally, those platforms will deliver to the end users using different technologies. And in the over-the-top case, it'll be HTTP based today, so HLS, Dash, etc. So how can we address this in media streaming mesh? Well, I guess I'd say, firstly, if you look at the far left contribution, the challenge there that we're going to have in the cloud native world is that these platforms aren't very cloud native. They are real hardware. But as we get to the studio and some of the mixing functions, such as adding on the score, that feels like compute. Certainly once you get to then encoding that uncompressed stream in different formats, well, that's very much a cloud native use case, I think. And so rather than having your encoder sitting right next to the studio, as in this picture, perhaps the encoding could be happening on pure software platforms running in the cloud. From there, distribution to the different caches, head ends, etc. That feels, again, like something we can very easily address. One of the nice things with proxying is that the proxies that we build can handle fanning out the traffic to multiple destinations, but can also add things like forward error correction or send on diverse paths, etc. Finally, delivering to clients, I think that's going to be a challenge in the short term, at least, because my television is probably not getting an update anytime soon. There's always this issue of firewall traversal as well, of course. We have prototyped using RTP over QUIC. So QUIC typically gets through firewalls, at least at home, and we can stream RTP over that, for example. Longer term, there's some interesting stuff coming. The ITF is working on there's a working group called Media over QUIC, and looking at more native ways to carry real-time media and other media over QUIC. So not using RTP at all, but layering directly on QUIC. So QUIC, just as a quick detour, QUIC, of course, is the underlying protocol for HTTP3. So that's really the next generation of HTTP, and it's UDP based. Typically, you do have error correction like with TCP, but that's pluggable. And so one of the options is just run datagrams over QUIC. So IoT is another use case. And this is, for example, if I go and buy sushi these days, I might go into or anything else really, I might go into a shop. So there's one chain I'm thinking of in particular here in the UK, Itsu. You go in there, and it used to be that you'd go to till and pay. What happens now is you just go to a machine, like a flat screen with touch screen, and you put in, okay, I've picked up this sushi, I've picked up this drink, whatever, and now I'm going to pay. There's no human involved at all. So I have to assume that I'm being watched on camera so that I don't steal stuff. And I think this is another use case where, so you might have lots of these shops, each with a few cameras, or you might have a very big site like an airport with thousands of cameras. Now, each stream could be consumed by multiple applications typically, and sometimes humans. So the issue, I guess, is that cameras are very cheap. You now have thousands of them, but humans aren't getting any cheaper. And of course, ML is a thing. And so what you can do is having these machine learning based apps that are watching all the different cameras. And if they see something that looks unusual, then perhaps they forward to a user, like a human user, who can take a look. So rather than at an airport having 10,000 cameras and an army of 1,000 people watching the feeds, you can have a much smaller number of people only watching the stuff that matters. So what you do is you put proxies near the cameras, you put proxies again near where the viewers are or the ML apps, and that way you build an optimum replication tree through the network. And today, typically, IP multicast gets used for that. And that's a challenge because really multicast is designed for things like IPTV, where you have a few sources and a lot of receivers, less so for things where you have thousands of sources, each with just a handful of receivers. And really the problem there is a lot of state gets pushed into the network. And as a network engineer, we don't really like too much state in the network. So today with what we think of as internet streaming, how it works is simply that my browser connects to a server, gets a list of media segments. Now, if it's non-real-time video, that list could be all the segments of the video. But for real time, of course, the challenge becomes you want to give the user only one or two segments at a time so that you're not too far behind, because these segments are typically a couple of seconds of video. They're basically files that your browser is going to pull. But the challenge is if you don't have a few of those, then if something gets stuck, so for example, there's a packet drop, TCP has to slow down, there's your challenge that you now can't get your video stall. What I've seen sometimes with some of the stuff I've tested is that literally the screen will freeze, and then you'll see it running faster than real time. And so these footballers look like they're in an old black and white movie where suddenly everyone's running really fast. So that's, again, talking about media over QUIC, that's one of the benefits of QUIC, of course, is that because the congestion control is something you can modify, and you can do clever tricks like, for example, putting each video frame into a different stream, still having error correction. And then if something goes wrong, you just lose that one frame and then you can carry on rather than the whole stream blocking. So how does it work with, for example, a security camera that's running? I've got one here at home, which hopefully I'll show you in a bit. And basically what you do is your app, so I'm using VLC as my application. VLC will connect to my camera. It'll ask for a URL. What happens then, though, is that the camera and VLC effectively negotiate UDP ports for each stream that's going to be sent. And then that media gets sent to VLC over UDP. The challenge there is that those UDP ports aren't known ahead of time. Now, this becomes a challenge, of course, for Kubernetes because, so for example, kubeproxy, you're doing NAT, and the only way you can do NAT is if you know what streams you're going to NAT. And so these dynamically assigned ports become a problem. And what you'll see if you try and run this stuff through kubeproxy is that it will fail initially attempting UDP. It will then fall back to using TCP, where the media actually gets encapsulated on that same TCP stream. So now you have more delay. And so another approach that we see for video over IP is multicast. So I mentioned that earlier in the context of security cameras, but another example is Studio, where what you'll see in studios running media over IP is that typically the camera or whatever the other source is will be sending on an IP multicast group, and they have a receiver, which could be an encoder. The challenge is the receiver needs to find the camera. So there are various different ways you can do that, but the common way in the studio environment is that you have a controller. The controller basically connects to the sender of the video and says, okay, what media information have you got? It then connects to the device it wants to receive, tells it what it needs to get, and then the receiver, in this case, would join an IP multicast group and the traffic would flow. So again, apologies for the misalignment here and the lack of the build that I plan to have. But so in terms of connectivity in Kubernetes and what your different options are, obviously the default option is just to use kubeproxy and node port. So this is just default NAT-based approach, which works fine for TCP, HTTP, and UDP. But the challenge is that, as I mentioned before, with the port negotiation, it can't work for real-time media because it can't know those ports ahead of time. In the world of web apps, service meshes, load balancers are very popular. those are great for TCP. They're fantastic for HTTP because you can now do URL-based load balancing, etc., where you say, okay, www.foo.com customers goes one way, but products goes another way, that sort of thing. Typically today, they don't support UDP, but that's coming, but I think largely driven by the requirement for Quick for HTTP3. But again, they don't support real time. So another approach is to say, well, let's use host networking. So let's just run everything in the host network namespace. And that works absolutely fine. But the challenge, of course, is that you only have one instance of each UDP and TCP port. So now really you can only run one media pod per node, which isn't very cloud native, I guess. And if you're running on virtual machines, it might be doable. And I've seen people do that. But if you're going to run on bare metal, that's going to be a problem. So the media streaming mesh approach says, well, let's focus on that real-time media. Now, since it always gets encapsulated on top of something, typically UDP, but it can also be TCP or it can be Quick, well, we can proxy at those layers as well. I've colored that star for HTTP in yellow just to show, we can support Quick, but not full HTTP3 typically. So really what we're saying here is that perhaps you should look at using things like service mesh on the top left for your web type apps, and then use media streaming mesh for those streaming type apps that are real time. So let's look quickly at our software architecture. So what we have is a Kubernetes cluster here. We have a bunch of different services that we run. So we'll come on to what those do. Then we have some daemon sets that we run on each node, each worker node in the cluster. And then the media pods themselves have some things that we run. And so let's go into each of those components now quickly. So we have a permission webhook, and this really was something we added initially when I started building this. As you may have gathered, I'm very much a network engineer, not a software engineer, and I didn't know how to do this stuff. And so what I was doing was I was manually creating things like an additional pod in each. So in the YAML file, I would, as well as having my app, I would add an additional container to that pod for my little stub proxy, which I'll come on to what that does. Also, I would add IP tables rules, etc. And so one of my colleagues helped me out with two things. First is the submission webhook. So when we get a pod deployment event, effectively what it does is it uses an admission webhook to automatically inject that MSM stub into the media pod. And we do that with a custom label. So we just annotate the pod with a label that says, media streaming mesh true, effectively. Then the CNI plugin. So in this case, the other thing we have to do is add that IP tables rule. So really, initially, all we need in the RTSP case I'll show you is one IP tables rule, just to take that control plane that I showed a few slides back and divert that from the media app into this stub proxy that we have. So that's very much similar to what how Istio would configure Envoy with IP tables to get stuff into the Envoy proxy. This runs as a change plugin, so we're very much plugin agnostic. It's CNI agnostic. We can run with any of the CNIs out there, but we just have this little micro CNI effectively to add the IP tables rule. And again, it uses that same annotation. So the next thing to talk about is the control plane. So what we've done really is to split the control plane from the data plane. And the control plane, what we've done is we just run that one per cluster because that minimizes our footprint. We're using gRPC as our southbound protocol to control the RTP proxy, but also to talk to the stub proxy that we have in each pod. It then talks to the Kubernetes API and to DNS, typically for things like mapping a URL to the actual Kubernetes endpoint. So we'll come on to how that works in a bit. We've written all this in Golang. I guess one benefit here is that we can leverage existing libraries. So the RTSP demo that I'll show, we've used Go RTSP lib. So then we haven't had to write too much code on top of that for the RTSP protocol itself, and all that kind of RTSP encoding is taken care of by the library. Where we're looking to get to with the control plane is to make it very much pluggable. So the thinking here is that we'll have the protocol itself, whether that's RTSP or something else, will simply be a plugin. We'll have this URL handler that does that lookup on, as I say, to take a URL with a domain name or whatever and find a Kubernetes endpoint that matches that. We have the handling for our stub southbound, but we've actually split the control plane out from what we're calling the network controller. And the reasoning here is there are two things you need to do. One is to run this dynamic protocol that is typically used certainly outside of the cluster. I think longer term inside the cluster, what we may be able to do is go to a much more SDN kind of approach, so software defined networking sort of approach, where we literally have APIs and we say, well, I want to add a stream onto the network, and we just program that directly through the network controller. So how we do that is we have this stream graph, and that gets written to by the control plane, and that's going to be persistent. So our initial implementation, we have that in etcd. We're looking at maybe using Kubernetes custom resource definition, CRD, for that. And so if, for example, the network controller restarts, because we just have one instance of that running, that doesn't matter because it can just pull that data from this persistent stream graph when it comes back up. To handle control plane restarts will be a little bit more complex in that we'll have to store the state of each of these sessions that are coming from the media pods or from external apps. One of the benefits, I guess, of using gRPC between this stub and our control plane is then we don't have to worry about TCP session state. So in order to have that redundancy, rather than having to mirror TCP session state, we'll only have to worry about effectively what are the active sessions that we have and just store those. And so the rate of change there is pretty low. It's really just, for example, if we were using media streaming mesh as the underlying technology for this, my video stream's going on for, 45 minutes. And so it would literally, there'll be one write to that table saying, okay, this stream is now running, and it would only be 45 minutes later that it would be pulled down again, rather than constantly keeping the session state. So that's how we'll handle redundancy. It's how we want to handle pluggability. I think one of the keys in all of this, as with any open source project, is that we need to make it easy for people to contribute. So the thinking here is that if this plugin has fairly well specified interfaces to the rest of the system, then anyone can write their own plugin and can bring that and just plug it into our system. But equally, by splitting these two out, if somebody has a whole existing protocol and it's not written in Golang, for example, and they want to contribute that, that's entirely possible too. All they would have to do is write to the stream graph, and our network controller can pick that up. So the stub, so this is the stub proxy. So this is kind of like our Envoy sidecar, but it's much, much smaller, which is why we've called it a stub. I've written it using Rust. It's asynchronous. That was an interesting challenge getting my head around that. But it's only about 1,000 lines of code. And it has two functions, I guess. The first one is it terminates that TCP connection from the application control plane. So in this case, it doesn't even know that what I'm doing in this demo is RTSP. It just sees it as TCP packets or TCP stream. The benefit there, as I've mentioned, is that we've now decoupled that from the control plane using gRPC, so we don't need to worry about TCP session state. And of course, that can be encrypted. In fact, we can even then handle remote nodes coming into our control plane, because the control plane can effectively be an ingress, or we have an ingress in front of it that terminates that gRPC. But it can also intercept the data plane. So in the RTSP case, we have some code to handle this interleaved data that I mentioned earlier. In the case, for example, I said with kubeproxy, where after UDP fails, it'll try interleaving everything on TCP. Now within the pod, we're quite happy to do that in many cases, because of course, we're not going to drop packets inside the pod. But then outside the pod, going through the network, we want to run UDP so that we can do all the replication, so we can handle packet loss, etc., in a way that doesn't delay us. And so the stub will handle interworking between those two cases, and that's running in my demo. We'll also look at things like SPIFFE Spire, policy, open policy agent, etc. Basically in that we plan to encrypt everything through the network from the proxy, but what we still need to do is end-to-end authentication and authorization. So the RTP proxy, so this is, again, I mentioned that we split the control plane from the data plane, and that we have one control plane per cluster, since we're handling things at a cluster level in Kubernetes. What we've done with the data plane is we deploy that as a daemon set, so one per node. So it runs in the host network namespace, and it will handle both east-west and north-south traffic flows. To handle the north-south control plane, we have a stub that runs alongside it. But for the data plane, it handles all of that itself. From an RTP perspective, for those who know the real-time protocol, this is specified in RFC 3550, and they call it a translator. So in this case, because we're terminating the UDP, we can do things like unicast to multicast, v4 to v6, private to public addresses, tunneling, converting MTUs, etc. We can handle, as mentioned earlier, encapsulating UDP, but also TCP or QUIC, and then also proxying at those lower layers. One of the great things in proxying everything is that we can minimize our attack surface. So firstly, we're only opening up the ports that we need. In terms of the data plane, we open ports very much dynamically. Once that negotiation that I showed earlier happens and it says, okay, this app is using this port to talk to that app on that port, then we open up that pinhole. But also the proxy itself, the goal is longer term to make this pluggable, which I'll come on to. And for example, you could have plugins that do things like validating that the flow is actually valid RTP, that some of the RTP fields are correct, and that sort of thing. Now that's the future. At the moment, we have a prototype we've written in Golang. I really must get around to very soon rewriting that also in asynchronous Rust and providing that framework for the plugins. The performance is a bit limited today because of the Golang implementation. Initially, actually, I thought garbage collection was going to be my big problem, but it seems that kernel sockets are a bigger issue. And what we're looking to do in Rust is support DPDK, so Intel's Data Plane Development Kit, for talking to the NIC, which means you can run in polling mode, very high performance, low latency, and then probably use eBPF to talk to the media pods rather than going through the CNI there. So that'll maximize our performance both towards the network and towards the apps. So the goal there is to have this basically plugin-based architecture where on the ingress, we strip off those transport headers. Then we have a configurable filter chain. So for example, we might add forward error correction. Initially, we want to do that perhaps to every destination. So we'll do it before we replicate the stream. Then we do the fan out to the different destinations. But then it might be we have different encryption keys for each of those destinations. And so we'll do that after the fan out. And then we add on the relevant headers again to transport. In terms of traffic coming from the client, so typically the RTCP, so we have, as well as the real-time protocol, we have this companion protocol called the real-time control protocol, which if the stream goes from the source to the receiver, you actually have RTCP packets in both directions. So you have sender reports and receiver reports where they're talking about what's the quality of the stream and that sort of thing. And so that RTCP traffic coming back, as I mentioned earlier, in terms of security, you might want to validate that it's from the right send, that it talks about the right source. You might want to check also that the client is the client you're expecting. So in your STEs, I think you'd have stuff like, this is Giles's laptop. I've certainly seen that on packet dumps. You might then want to aggregate things where you have multiple clients, so you just send one report up to the server. And the other thing in all of this, of course, is monitoring. So everything we do, the goal longer term is to monitor what's happening, to be able to detect things like packet loss, jitter, etc. So the demo setup, we have a fake camera feed I was going to show you with a football match. So because I don't have a football match going on right now, I just built that as a fake feed that runs in a video stream pod. The client will connect through the control plane. It'll negotiate effectively with that server, which will then send the stream back. It will convert it from a pure TCP stream to the normal RTSP case where the video goes over UDP. That will flow through these RTP proxies to the client. If you have multiple clients, the great thing is that effectively they're joining at the edge. So this is like IP multicast, but happening a layer up. So the server only has to send one copy of the stream, and the same would be true with a real camera. So let's quickly show that. I will hopefully the share screen will work now. I need to quickly. Great. So I need to unmaximize this, I think, before it's going to let me do that. Right. Not this one, it is this one. Sorry about that. Right, so this was a football match that took place a few weeks ago. And on the top left, I'm showing VLC connecting in real time. It's that camera feed. In the bottom right, I'm showing an HTTP live stream. You can already see there's a lag there. So the ball's already been placed, and then it's getting placed a few seconds later on the right-hand side. And as all these big matches do, this went down to penalties. It was England versus Brazil, and this is the winning penalty here. So again, the lag I'm showing on the right-hand side probably isn't long enough for someone to text you that there'd been a goal. But of course, this is only one stage of HTTP streaming. It's not going through a whole CDN. So you can easily see how that would build up. You may see a little bit of glitching on the video feed on the top left. Again, this is this Golang based proxy. Certainly, once we get that moved over to Rust with DPDK and eBPF, we'd expect to see very high throughputs of hundreds of gigabits per node, that kind of stuff, and without packet loss. So that's the live demo. If I come back to hopefully this comes back right, great. So, sorry. Then we also have this live demo. So the second demo I was going to show, this is literally a camera that's sitting here in my study at home. So basically, a client's connecting out to the camera. It's then pushing that data into a server just to create that kind of feed. It's an interesting one. I think longer term, where we'd like to get to is that RTP streams themselves get defined as CRDs and Kubernetes, as I showed earlier with the stream graph. So getting to a point where we don't have to push stuff into a server, we can push it straight into, effectively straight into Kubernetes and have the proxies proxy it without needing to store it at each stage of the media chain. And other than that, it's pretty much the same. And again, there could be multiple clients connecting in, and those clients would effectively just be joining at whichever edge node they joined. But if, for example, another client came in and hit this node, then that would be replicated out through this proxy. Again, if it hit this node, it would go through that proxy, etc. So this is all running in an infrastructure called Great Bear, which runs on top of K3S. It's running in AWS. I will just grab that one. It is, 1 second, ISS VLC. Right. So here we have this one. I'll just go sacrifice and check in. The live demos are always a bit risky, aren't they? So here you can actually see me from behind in my study. I apologize for the mess in the study. There's a little bit of lag on this one because the camera's only running a few frames per second. And we're having to use TCP to connect to that camera because it's sitting inside my home. But you can see that's all running pretty normally. And that's live. And again, if you were to connect to this URL from where you are, you would find that that would run absolutely fine as well. And it would just be replicating in the edge. Great. So hopefully back to this. Yes. So really, where are we trying to get to with this? Well, I think the key thing is that we're looking for, I guess, most of the same benefits that you would see from service meshes in the web applications world, but then really applying those to real-time media apps. So I guess the top half of the screen is very much those same benefits. So observability, which for us means measuring jitter and packet loss largely. Of course, there are other things we might want to do, but that's I guess absolutely critical that we can see, are packets getting lost? Are there delays? All that sort of thing. But we'd also want to be able to actually see that graph and be able to see, okay, we have this sender for a given stream, and here are the receivers, and here's where they're located, and here's where we're replicating traffic. In terms of security, as I mentioned earlier, authentication and authorization, but also, of course, encryption. So running node to node, we'd either run SRTP, which is the encrypted RTP, or we might run RTP over QUIC, and then we get the encryption from the QUIC layer. But then also looking at the bottom half, these are things that I guess are really unique to what we're doing. So I've talked about optimal stream replication already. So that's a key thing in terms of how do we distribute the video and how do we get it out to where it needs to be with really, as on the bottom right, minimal cluster footprint, but also with optimal stream topology. And how do we make sure that as well as measuring that jitter and packet loss, that we've actually minimized it? So as I mentioned earlier, using things like Intel's DPDK, using eBPF, using asynchronous Rust, getting that really high performance so that we can get that low latency, that consistent jitter, and not drop packets. But then also by having that pluggable data plane, for example, we can add on those things like forward error correction or NAC-based error correction or sending traffic over diverse paths. So we have different ways to make sure that we get traffic to where it needs to go. And yeah, keeping this footprint small. So having a control plane per cluster with the ability to have a data plane per node, not only for nodes in the cluster, but having remote nodes that would leverage that control plane in the cluster, which of course you could see that longer term as being a SaaS type approach where you might have the control plane running in the cloud, but then your data plane running on the premises. And that stub sidecar I mentioned, very low footprint, and we can really optimize that for the application we're running as well. So, for example, that RTSP code I've got that does the interworking between TCP and UDP, that wouldn't be needed in a more general case. So really, and I can see I'm finishing a few minutes early here, but maybe that gives us some time for Q&A. This is very much an open source project. It's pretty early stage. I think what we're looking for is for people to help us. Our goal is to enable real-time apps to be fully integrated in cloud native. And to get to that point, I think that the goal is to have this platform with plugins both for the control plane and the data plane to make it easy for people to contribute. But really, ultimately, as any open source, it's all about community. It'd be great for people to help out, whether in terms of giving us requirements or whether in terms of actually helping write code. The URL's there for GitHub. So there's a whole bunch of different repos there. And my contact details are in the bottom right. And there's a QR code there also, which I think takes you to our public website, which also then will link back to the GitHub and links to our Slack channel and that sort of thing. So yeah, please do get involved. Please do take a look. Tell us what you think, good or bad. And as I say, it'd be great if people were willing to help out in any sense, whether it's use cases, documentation, code, etc. It'd just be really nice to see a community building up around this. So apologies again for the slight issues here with PowerPoint in this system. Had I known, I think I'd have probably just used a PDF. But there you go. It's as I say, I was testing things out properly, which I failed to. But yeah, thank you, and hopefully let's have some Q&A.
Fantastic. Thank you for that, Giles. Yeah, guys, if you want to post your questions across Giles, there is a Q&A section. Just click on the tab, type the questions out there, and then I'll relay them across. I mean, honestly, first thing I kind of like was sitting there listening to that difference in the timing that you're talking about. I immediately thought of these. I don't know if you've seen the documentaries. It's people that basically make a living off of playing betting sites against themselves, essentially on like tennis
Oh yeah,
courts,
yes.
right? Yeah, where they relay the info back to a person. I was like, damn, betting companies would absolutely love this technology because it would quickly they would shrink that gap, right? It would make it almost impossible to exploit.
Yeah, and that's it. And I think if you're into in-play betting, you're certainly going to want to watch on a real-time feed, aren't you?
Yeah.
It reminds me. There's an old New Zealand. There's an old movie. I think it was from like the '60s or something. It's an ancient film. I think it's called Came a Hot Summer, and the whole plot of that film is about that, like somebody managing to get information about the result of a horse race
Oh, okay.
before the bookie in the town where they place the bet. And that is the classic thing, isn't it? Information is valuable depending on timing, and I think that again, when I started this off, I was looking at things like stock market feeds, because ticker feeds. I mean, those are the classic thing where you want low latency, but of course for those, it turns out that people are talking microseconds, not milliseconds. And the question then becomes, can anything that's based on a standard Linux kernel give you that kind of performance? One of the challenges there, of course, is that ends up with, from a developer point of view, people running two whole development teams, like one team that does all their non-exchange kind of stuff. I know a guy who runs infrastructure for one of the investment banks, and he was saying that to me a while back. That's one of his problems, is he literally has a whole separate team. He'd do all that really hard real-time stuff. But exactly, I mean, how can we ever get that cloud native? I mean, it's running literally on dedicated hardware that's sitting, within a few hundred meters of the London Stock Exchange or whichever other stock exchange, because speed of light's a problem for this as well. And that's going to be a real challenge for us. But for the football, I think being within a second or two is fine. I don't think I need microseconds,
Yeah, maybe you're like 2 seconds later than Bill to like tweet something out about it, but I don't think outside that is going to hurt too much. I think the other cool thing is where this could be beneficial to businesses, right? Is like if you imagine like premium models where people want an even quicker, they pay for that, right? They pay $5, $10 a month to
Yeah.
get it just, several seconds sooner. It sounds absurd to
Yeah.
some of us, that casual audience members, but there's plenty of people that need that
Yeah.
info
And
on drip.
there are one or two businesses out there trying to do that kind of stuff today. I think again, what this could do is drop the cost to do it, because you can do it on more generic infrastructure.
We do have a question coming in from Mikhail. They ask, do you plan to implement the HTTP-free underlying infrastructure? What can be the challenge of that? And considering it's using QUIC, a multiplex transport protocol built into UDP.
Yeah. Yeah. As I think I said earlier, I don't think we'll implement HTTP3, but I think we will implement Quick. So we already have, we've tested out doing RTP over Quick, but I think as this IETF media over Quick protocol sort of coalesces, I think we'd look to move into that, and that gets a bit interesting. Of course, that's no longer RTP based, and for that, I think their current thinking, there's a bit of a debate, I think, over whether to run directly on Quick or to run on HTTP3, but only partially using HTTP3, if I remember right. The other interesting debate there is between this kind of, I think I mentioned, sending every video frame on a separate quick stream, which then means you only get head of line blocking for one frame. But of course, the thing is with video that you're typically using something like MPEG, where you have like these different types of frame, and it's only the iframe that's standalone. The other frames are all sort of deltas and that sort of thing. And so the other approach is to say, well, let's use a stream for each what they call a group of pictures, which might be one iframe, and then all the kind of predictive stuff and delta stuff after that, such that again, the head of line blocking would just affect that. But if you have, I think it's typically a couple of iframes a second on video. So if you did get packet loss, you might have a half-second glitch, but that's probably not the end of the world. But again, it's interesting what, just to see that kind of coming together. And I think what's really interesting is that, okay, I need someone like me, is that longer term, with Quick and HTTP3, maybe we see these two worlds of the web apps and the media apps coming together at last. And so that becomes the solution. But one thing is, it is very different with media compared to the web apps. So you might see service meshes doing HTTP3. Well, one of the real differences is that with web apps, typically you've got this very high request rate because you're, getting all these different pages and images and stuff, and each one of those is a separate URL. And as I think I mentioned earlier, one of the things that's different here with media is that you have these quite long-lived streams, and so you can have a kind of different architecture. But also in terms of how you scale it out. So instead of it being, well, I'm going to have a whole bunch of replicas sitting behind one service, and each of those replicas is basically serving the same stuff, and that's how I scale out horizontally. What you're going to do is have a hierarchy of, effectively, by having a cache on each node and then multiple nodes in the cluster. That way, that one stream can basically be replicated by the node it's on, and then can be replicated again by the nodes that users are connected to. And effectively, you can do that sort of layer after layer of it. So it is quite a different model, and I think that's where I mentioned that I kind of want to get to the point where streams themselves are resources in Kubernetes. And I think the interesting thing around all that is going to be, do people care enough? Like, are people happy to just have a platform that runs web apps, or do they want to bring all this other stuff into Kubernetes as well? And I think the world there is changing. I think a couple of years ago, nobody cared, was my impression. But the fact that I did a keynote at KubeCon a month or two back suggests that people are starting to think this is important.
Yeah, especially when you highlight the kind of like cost efficient approach to it. Like we just highlight a few benefits that certain businesses would see in it. It's just, you have to make the use case, right? And once you have that, boom, the doors kind of open and users flood in.
Yeah. And again, the football's a great use case to get people's attention. I think to some extent the IT cameras might be a bigger thing, but then nobody really wants to talk about spying. But also actually we're doing a lot of work in that professional media space with partners and discussing with people, because that industry has started to make that transition from proprietary not proprietary, but non-IP interfaces. So they have SDIs, this digital interface to a camera, and they're moving from that over to IP. What they haven't yet done is made that move to cloud native. And so I think there's some real interest there.
definitely sounds like an interesting subject. I'm just going to pop this back up on screen for people. So remember, folks, if you've got any extra questions to throw Giles' way, he seems like a very approachable guy. I'm sure he'll be willing to take them. And contribute wherever you can. I mean, this sounds like exciting stuff. I agree. I think there's definitely something here, and I'm glad to see people are starting to pay a little bit of attention to it. But Giles, my friend, our time is up. It has been a pleasure.
Not a problem.
I look forward to seeing
Likewise.
how this develops.
Thanks so much.
Thanks, guys.
This is all we got. Remember the revolution in our minds. This is all we got.
Lock me out of this life institution. I am angry and high on illusions. Yes, I hate, but it's not a solution. Try my best, but I'm just a human. Oh.